Ever. The maximum torque now is 1.15, the mean torque. Okay, now then you use the maximum torque in your following this thing. Now the one to know here, the question is slightly, it's a design type of a question. Determine the minimum diameters of the shaft if the angle of twist must be that and the maximum allowable stretch is that. So you've got two types of constraints or criteria in this type of a question. Okay, so that's why they're working with the maximum torque over here. Right. So you can see now if you're using the shear stress as the equation, you'll end up with a diameter of 83,1. Okay. And if you're using the angle of twist 1 degree, or whatever they gave you as a constraint or design consideration. Limiting factor just means design consideration. You can design this diameter of the shaft on two theories. One is a twisting of the angle of twist, and the other one is a stress one. So you don't know what is the minimum diameters. You got to try out both. You're going to get two diameters using different equations. You can see one is 83,1 using the stress equation or stress part of the formula, and then the other one is the angle of twist part of the formula, and you end up with 99. See that? Now the question is, which is the minimum diameter? Now you must be careful here and listen carefully. The minimum diameter is not the smaller one. It will be the bigger one because you have to consider safety. If you say the minimum diameter is 83, that means yes, for shear, it will not shear, but it will violate the angle of twist. If you use 83 in over here, you put in 83 in this formula, you see your angle of twist is not going to be 1 degree anymore. It's going to be 1,5, 1,8. And the question is not that. The question tells you the maximum angle of twist must be 1. So I hope you understand the logic. So the minimum diameter will be the greater diameter, because the greater diameter will satisfy both criteria. It will satisfy the angle of twist and it will satisfy the shear stress formula. Okay, I hope you make notes of that, eh? Right, people, like we had yesterday now, you get shafts in series and shafts in parallel. You get the exact same thing now with torsion. Same theory, nothing changes. The only difference, instead of forces, you talk with torques. So you can get now torques that are applied intermittently along the axis of a shaft, and you can get torques that are applied at the outside ends, like I showed you now. Right. The theory is nothing changed, only thing the force changes to torque. The hand thing that I taught you yesterday, summation of torques to one side of the section. You need to find out the resultant torque on each segment. Exactly the same rules as we've done yesterday. That's why I teach axially loaded members and I follow up directly with that with torsion because they're identical. Okay, you should be a master in this thing, eh? Very easy. Same type of way you solve these things. Sometimes you may get a ratio equation, put it into the second one you never use, and you solve mathematically. What we done yesterday applies 100% what we're doing today. All right. You can see here now, okay, it's a comparison type of example, a bit of mathematics type of thing. Simple stuff. Here we are. Okay, same like we done yesterday. Check here now. Instead of forces, we got torques. T1, T2. What is important now? The direction. Clockwise or anti-clockwise. Remember we said clockwise is positive torque, anti-clockwise is negative torque. You put your hand at the section, consider everything to the left-hand side of the section for the resultant torque. Any torques that pass through the border or the hand vanishes. Same rules as yesterday, yeah? Exactly the same thing. So again, you got to find equilibrium for the unknown torque. The summation of torques along the x-axis is equal to 0. Find the unknown torque value. After that, now you use your hand, you apply it to each side, and you look at the torques. Now it's not a tug of war as such, but it is a tug of war in torsion. So for example, if you want the resultant torque at VV section, the resultant torque is going to be now the summation of torques to the left-hand side of V. So it's going to be T1, which is positive T1 minus T2, and that will be your answer. Okay, again, the rules are the same. Wherever you got a torque, you will have a letter. Wherever you have a change in cross-section, you will have a letter. Okay. Here we are, what I'm telling you now. Okay, same thing, all I'm explaining to you in a few sentences. Formulas, total angle of twist. We're not talking change in length now. We're not compressing and expanding, yeah? Yeah, we're twisting. So total angle of twist is equal to the angle of twist in each section, like we done yesterday. What is the angle of twist? It is got from the normal formula. T upon the first formula I gave you the three things. The general formula, you get it from there. Very, very easy. Are you guys with me? Indication? Yes, no?
Yes, sir.
Okay, all right. Can you see the similarity between torsion, what we're doing today, and what we done yesterday? Almost identical. Only thing, the force is replaced by torque here. All right, almost identical. So write down, if it's a member in series, write down this formula again. Remember the rules. Total angle of twist is summation of angle of twist on each side. There's another problem here to give you, like we done yesterday. Okay, yeah, there's no unknown force. You don't have to worry about equilibrium now. Everything is given to you here. You can just use your hand rule and work out the net torques on each side. So you can say torque in section AB, torque in BC, torque in CD. Okay. So I see they're using equilibrium and all that type of thing. They're just testing for equilibrium. You don't have to worry about that one. Only when they give you an unknown torque. If you don't know one thing over here, then you must apply it. All right. It will come as you practice. It's straightforward stuff. Here's another type of one. The internal diameter is to be 70%. Okay. You write these things mathematically, eh? Right. The torque, end torques. Read the question on the top. This is a second case like we done yesterday. Yeah. Remember we had forces at the end. Easy one. There we are. So the torque in the steel shaft is equal to the torque in the aluminium shaft. In series, eh? You can have different materials or different sections. One is 10 millimeter, one is 20 millimeter. So that is your two governing. So now you have three governing equations in torsion. One is the first thing you're going to write is a general torsion formula, T upon J star upon R, G theta upon length, that you'll always write. Then read carefully, is this thing in series or in parallel? If it's in series, then you write down your two governing equations, depending on what class it is. If it is this thing, intermittent load, you got your equations there. If it is your end loads or end torques rather, you got your equations here. See that same thing as at the top. Total angle of twist is summation of angle of twist on each section, like your textbook is also showing you. End loads, the torques are the same. How we had yesterday, the force is the same throughout the shaft. If it's end loads, same thing here. Very easy, eh? Right, because here they're writing it mathematically. The angle of twist of the steel shaft is 0.7 the angle of twist of aluminium. You call that equation 4. I hope you're listening what I'm telling you, eh? Call that equation 4. Now you got 4 equations and you solve them mathematically the way it's easiest for you. No problem on my side, you get full marks. All that others is simple mathematics, school maths, eh? Nothing complicated. Right. Actually, yesterday now, as we had members in parallel, remember we had one pipe inside another pipe. You got the same thing here now. Okay. The same thing your textbook is also explaining to you. Right. The rules are, of course, opposite now, like we done yesterday. The governing equation. So now the total torque. Remember this thing here, people, there's 1 and 2 over here. Okay, they're taking it out so that you can see. But remember, they are in parallel. They're not series. The diagram is a little bit confusing here, but read it carefully here. They're trying to show you that pipe 1 over here is inside pipe 2. It's not a series member. Shafts in parallel. Okay, so it's not, if I were there, I would have made a cross section, okay, of the stuff. But it's not in series, in parallel. Shaft 1 is inside shaft 2. So the total torque now is a summation of torques on each shaft. How you know what the torques are? You use a general formula. Remember those 3 things? Any two of those combinations you can use depending on what the question give you. Substitute it and get the torque. For that section A or section 1. For outer shaft B, exactly the same formula. You may have a different diameter or different material you use. I hope you guys get the hang of it. The general formula in the front, you apply it to any section or any segment of your shaft, whether it's series or parallel, doesn't matter. Only thing that's going to change is the diameters. Of course, the J value is going to change. The length can change. If it's different materials, the G value will change. Okay. Very, very simple stuff. So I'm just teaching you the principle here. After that, it's simple mathematics. The other one is your theta, the total angle of twist on any in a compound shaft in parallel, one inside the other, is the same. Like we had yesterday, the total change in length is the change in length in any section. Same thing here. Okay. And I think they're giving one question over here to explain it. Okay. You don't start like these people, huh? You know the rules by now. If you want a distinction, you listen to what I'm teaching you, eh? Start with applying your general torsion formulas like I'm teaching you, eh? You can see JD4, a bit of a torsional rigidity one here, they ask you the C value. Many ways of solving these things, eh? Because sometimes more equations you have, 3, 2, 3, 4 equations, the more combinations or permutations you have to solve it. Use anything according to maths. That's why they teach you maths. Maths is very important in engineering. Okay, use your maths they taught you in school at S1, S2, no problem on my side. But the way I mark students is I look at the answer. As a student got the answer or very close to the answer. Once he's got that, I almost give him full marks. I just scan very quickly up. Mathematically, he's right. He got his units, everything. 20 out of 20 for the question. Finish. I don't distinct. Dingle dangle. You with me? Long as you got the answer or close to the answer, you get full marks. Okay. Remember now that the units, always keep in mind that the units for torsional stiffness is Newton meter per radian. Eh? Just keep that in mind. A lot of students lose a mark in that. A lot of students. Okay, watch out for the units for this. Watch out for the units of moments. I can't understand why students get the moment unit wrong. Moment is a force times distance, Newton meter. Students put Newton stroke meter. It's not that. Stroke, that's different thing. Then the moderator -1 mark. Unnecessarily. Okay, so the formula gives you the unit. You can see you got torque, which is Newton meter, upon theta, which is angle of twist is radian. So what's the problem? I can't understand, students. It's a divide here. This slash means divide. If you got moment, it's force times radius, Newton times meter. So that's the units, Newton meter, not Newton stroke meter. That stroke means divide. Okay, some students lose 2, 3 marks unnecessarily. You're sitting at 37 in the exam. 37. Fail sub minimum because of 3 marks because you lose on units. Units are important, students. I don't know if I told you this. It's very, very important. Who is working at NASA? Americans. Ha ha. Americans are managing it, guys. They're not working there. People are working there. The guys from Nigeria, from India, from Germany, from Spain, from the rest of the world. The cream of the crop from the rest of the world. What units do these people work with? All different units. The guy that's coming from the UK is working in pounds per square inch. Guy coming from Nigeria or from China or whatever, working in different units according to the university or country. But they're all designing one rocket. They're working on one CAD system. So you have to be careful on units. They can't use different units over there in NASA. So the guy that's working in pounds per square inch, you have to be conversant on how you convert pounds per square inch to megapascals. You cannot put pound per square inch value in. Years back, a space shuttle fell down. Yeah, they're still falling down nowadays. You know one that North Korea fired a few weeks ago. One of the biggest missiles or whatever launches. Thing fell down. One of the reasons is units. The guy make a small mistake. Instead of kilonewton, I put Newton. and nobody check it. It's fine. Everything is fine. Just sign. Don't check. Happens. How much is a space shuttle or a rocket? You're talking billions of dollars, not Zimbabwe dollars. You're talking American dollars, billions, not millions. You're talking billions. And imagine those things fall down and catch on fire because of a stupid thing like a unit. But that's why engineers must be very, very particular to units. Very, very important. But that's why I fully support. If your units are wrong, you do not write Newton, kilonewton when you calculate your reaction, we will subtract marks. Don't worry. It is very, very important. Space shuttles have fallen down because of units. So I hope you understand where we're coming from. We have to teach you the right way so you survive in industry. Right, so that's all. Any questions on torsion? You have a chance to ask now. Ask me after the exams and test, then is no good. Anybody is unsure on anything?
I'm good for now, thank you, sir.
All good. Right. Okay, so there's some examples there in your textbook on page 126, guys. Example, you can see now, I think you know what to do now, guys. I don't have to tell you this all the time. Check your study guide, see what examples you must do. You know the procedure now. Go through the worked examples first, see if you can do them. There are solutions available. Once you feel that you are nice and strong and you're muscular, then try and do some of these tutorial problems to test your ability. Remember the golden rules for torsion. We do not work in degrees, work in radians. Write down the general torsion formula first always. Then depending on what type of a problem it is series or parallel, write down the two governing equations underneath that. Sometimes it's just one shaft. It's not series or parallel. Then you only got that torsion formula, the general one that you write down. Look carefully, convert the degrees to radians and solve. It's just mathematics, guys. Just choosing the correct formula and solving. That's what yesterday's section was and today's section was. Very, very easy. Come with practice, Right, so 6.2 and all these types of things you can do. 6.4 is a nice test and exam type problem. Page 127 of your e-book. 900, you can see you got 900 Newton meter, different directions of the torque. Do not let the diagrams frighten you, students. Do not let it frighten you. In fact, these diagrams are more helpful because you can see it in 3 dimensions. Okay, we're not working in 3D, We're only working in 2D, but you can see it. You can see the 900 is turning anti-clockwise. The 600 Newton meter is turning clockwise. Okay, use the same rule. Put your hand by B, put your hand by C, and work out what the net torque is on that section or that segment. Okay, they explain it to you here in your book also, if you read 6.4. Okay, so some movies here for you, 6.5 and etc. And I think you get the hang. Torsion assemblies, giving you a lot of things here. So follow more or less what I taught you. Don't go into too much detail. The textbooks normally do it because it's university stuff, but it's basically the same thing that I've taught you. All right. So I don't think there's anything else. There's a power equation there on page 139. Exactly what we've done. Equation 6.20. I'm not teaching you something new. All textbooks will give you the similar thing. Some movies again with shafts and gears connected to electric motor. Okay. Okay, you can go through that M6.19, statically indeterminate ones. 1 or 2 examples of that type of thing. M6.19, M6.20, the movies. All right, so like I say, multitask, see where your strengths and weaknesses are. You need more practice on certain things. By all means, go for it. I'm here to help you. Right, if everybody happy now on torsion. Okay, do not worry about stress concentrations and all that. Don't ask you. What I taught you is what you worry about. Okay, don't ask me things that I didn't teach you. Those things won't come out in a test and exam. So we stop there on page 150 or 151 of your textbook. Okay. Right. I think that's it. So now if we move on to the other section, which is called thin cylinders now. So let's put that up. In your textbook, it is called pressure vessels, chapter 14. So click on that one, please. Click on the arrow, and then you go to readings. I don't know why they call it readings, but as Americans have some funny ways of naming things. So the readings in the book is in your ebook is the theory, né? All right. So now we are on the last section for test and exam purposes. Okay. What I'm going to do is I'm not going to push the springs in today. I think it's about too much. I will do quickly on Wednesday next week. Remember, we got a tutorial section next week. So very quickly, 5-10 minutes, I will just run through the springs with you guys. Okay, it's not in the test and exam, so don't worry about that, but I will just do it quickly. And then after that, next week, Wednesday, it's the rest of the period is up to you guys for tutorials, things that you want, not for everything. Okay, specifically for your test, but you can ask me from anything, anywhere in preparation for your exam. But the following after that, you write your test on that this thing, and then not the following week, you write the test then on a Thursday morning. And the following week, I've already informed Dr. Bianca. He will start with you guys in the following week. I think that week of the 11th, as we discussed yesterday. Right. So next week, Wednesday, is your last opportunity to ask me anything on any tutorials that you're unsure. It is your period. Okay. Remember, it takes 2 hands to clap. I can teach until I turn blue or purple in the face. But if students do not ask questions, do not do problems on their own, you will never learn anything. Okay, no matter how brilliant or how good the lecturer is, doesn't matter. But until the student doesn't try the problem out, you will not learn much. Believe me. Told you from day one, engineers work with pencil, paper, and calculator. We do not read things on the screen. If you like that type of a thing, then you must go there to Arcadia campus, cooking and catering diploma or whatever. Then you just read. Today we're baking a chicken pie, 300 grams chicken, 1 teaspoon salt. You just read and you do it and you bake your pie. Engineers don't work that way, yeah? Okay, or you could do Shakespeare, drama, or whatever, if you like reading. Okay, so please, people, do the problems. Right, chapter 14 now. This is the theory on thin cylinders. Now, what is a thin cylinder? A thin cylinder basically is a cylinder which has to be hollowed, of course, where there is a specific ratio of the outer diameter to the inner diameter. So when you divide the outer diameter to the inner diameter, and if it is within a certain ratio, then it is classified as a thin cylinder. If it's greater than that ratio, then it's classified as a thick cylinder. So you also get thick cylinders, but what we are doing now is what you call thin cylinders, and it falls under the general heading, what you call pressure vessels. Now, there are thousands of examples in your everyday experience. One of the examples are your aerosol cans, your deodorant. That is also a thin cylinder. The fire extinguishers. Anything that contains a fluid. Remember, I never said water. I never said air. A fluid. Remember, a fluid can be a liquid or a gas. So the general purpose, people, of pressure vessels is to contain some type of a fluid, and most of the time it is under some type of a pressure. For example, your aerosol cans, your Doom can, all that type of things. Read there at the bottom on the label, do not expose to fire. Do not throw empty cans into the fire. That thing can explode, which is under pressure. Okay, so a pressure vessel stores fluid under pressure. That is what the general function is. A submarine, there Russia is attacking Ukraine or vice versa. Things happening underwater. Those submarines can be classified as pressure vessels. Yeah, aeroplane. Can also maybe design an aeroplane fuselage as a pressure vessel. Boilers. The kettle at how in your house, you're boiling water. All are pressure vessels. Okay, I think you get the idea, Right, so just you can read through page, I think it's R22, in your textbook. Read through all the theory there. There they explain. Do not worry about spheres. I will not ask you for spheres, so leave spheres out. Let's move out from that. I'll only ask you on cylinders. Right. Now, this example here or figure is important on page 502. Page 502 of your textbook. You guys must start investing in a laptop or something, Because I see everything is starting to go the e route now, electronic route. So I will suggest that you start investing in yourself in a reasonable laptop. You don't have to buy something very expensive, a reasonable laptop, eh? Okay, for your own benefit, eh? Right, so this is what we have here, people. We got a type of a cylinder, okay? Inside the cylinder, you have pressure, okay? And what happens now? The cylinder, when it's made up of a flat sheet of steel. They bend the sheet around a mandrel and they weld it along the longitudinal length. It's welded. Now you just got like a pipe. Now how will it hold fluid? You got to have covers like a kettle. How you got the cover? So they put two covers at the ends and they weld it in a circumferential jar with the weld. Okay, sometimes they use both. Most of the time they use weld. So that's how they make a pressure vessel. Flat sheet of steel or any material, certain thickness, they bend it under heat around some type of a mandrel. A mandrel is like a die to give you your diameter. Then they weld along the longitudinal direction. You can see here you got stress longitudinal. You see just now. And then they put end covers or end caps and they weld the end caps along the circumferential direction. And they have a small type of a hole somewhere where you can pump in your fluid or your gas or what. Okay, so that's how they do it. Tire of your motor car, of your bike, can also be classified as a pressure vessel. It's holding fluid, which is pressurized air or nitrogen if you're into drag racing, you know. Also, many examples, right? Longitude, you got two types of stresses that are formed. Normally three, but we only concentrate on two. So any pressure vessel is subjected to two main stresses. One is what you call the longitudinal stress, which is PD upon 4T. How you remember it? Longitudinal is a long direction. So you'll have the big number here at the bottom, PD upon 4T. Stress circumferential or stress hoop. Another word for hoop is circumferential stress. Is PD upon 2T. Because the circumference is the smaller one. So that's how you remember it. So there's only two formulas, PD upon 2T, PD upon 4T. Okay? And see what they want and then you answer. Right? They're explaining to you how to get the formulas and all that type of thing. There's the hoop one with circumferential stress in megapascal. So it's Pascal, PD upon 2. P is the pressure. D is the internal diameter. 2 times the thickness, which is the wall thickness in meters, eh? In meters, right? They're explaining to you how you get all these things. Don't worry about all these things. Only PD upon 2T, PD upon 4T. All right. Some movies and all here, they show you. They give you some examples here also in your book. Do not worry about all these type of examples like 14.2 where you got angles and all that. I won't ask you all that. All right. Let me just project the other this thing. Slides that I have. You're almost finished now. Where is my thing now? Right. And there. Put my slide up here. Should be that one. Oh no, that's the wrong one now. It's the second year. It's the second year. Let me just close up the ones we're not using. What is this now? Rotating cylinders. So that one can. There. Only got one. Right. Yeah. Share it again. Right. Can you see that? Thin wall pressure vessels, thin rotating cylinders. Can you guys see that? Yes, no. Can you see that? Thin wall pressure vessels.
Yes, sir, we can. Yeah.
Thank you. Thank you. All right. So here we are again here. Okay, same thing what your book is showing you. You can see the longitudinal stress acts in the longitudinal direction. Remember, there's a weld over here. And there's some welds here. You can see here, there's some weld along the circumference for the end caps. That's what I got over here. Okay. You normally talk about gauge pressure. That's the pressure inside your cylinder. But they put a gauge over there and it registers that. So that's why they call it gauge. Now, a thin pressure vessel, the thickness, the ratio of the internal diameter, small d to t, must be larger than 20. But that's the criteria. You don't have to worry about all this. But just remember that there is something also called a thick cylinder. Thick cylinder. Okay. Of course, if D over T is smaller than 20, it becomes a thick cylinder. If D over T is larger than 20, you classify it as a thin cylinder and you use the theory that I taught you. Okay. So that's what you're trying to tell you there. Same thing here. There's the two halves. Remember D? The circumferential stress is going to cause failure in the longitudinal direction. Remember what I'm telling you that, eh? The circumferential stress, the stress along the circumference, there's the P here. That's going to cause the cylinder to split in half. That's why they're showing you in two halves. So the circumferential pressure or stress is going to cause failure in the longitudinal direction. Keep that in mind. I hope you write it down, eh? Textbooks don't explain. Then the opposite is true for your circumferential one. It's the opposite. Eh? The longitudinal stress causes rupture. Okay, let me show you a diagram here. Show you the diagram here. Okay. Right. Here we are. There's the formulas again. Remember circumference? Yes.
Excuse me, sir. Yes, I'm sorry to disturb.
Oh, no problem.
I want. Yes. Can you go back to the theorem that you just mentioned?
That's
about
that one.
The diameter, the ratio of the D over T.
Yes.
Is it supposed to be larger than 20, the ratio?
Yeah. Yes.
Oh,
Larger
so
than 20.
okay. Then it will be thin walled.
Thin wall, yeah, yeah. You don't have to worry about it because your section is only thin wall. You do not have thick wall in your syllabus, so don't worry about that. Okay. Right, so there's your two formulas again. Okay, so stress circumferential. Remember, the circumference is a small one, so it could be PD upon 2T. That's how you remember it easily. Now, remember, these type of pressure vessels are governed by design codes. You don't just design these things. There's a whole code of practice because it is a critical item. You got to keep these welding bottles and cylinders vertical. You can't transport them. They're lying on the sides. It's a lot of safety aspect. These things explode and explode with a huge force. I don't know if you've seen these movies and all, Terminator and all, where they hit the guys with these, this thing, with these fire extinguishers and all. What force these things come out with? Almost like a bomb. So they are very, very critical equipment, eh? All right. Now we have to have factors of safety in it. It's a very easy section. This is the easiest section, I think, in your syllabus. All right. So the pressure in the circumferential direction, PC, is equal to 2 times the stress in the circumferential direction times the thickness times the longitudinal efficiency. Pass up. Watch out here. Remember I said the circumferential stress will cause failure in the longitudinal direction. That's why you got to use the efficiency of the longitudinal weld. Sometimes they put bolts there. They're connected for bolts. Those things have an efficiency. 90%, 80%. 80% NL will be 0.8. 90, 0.9. S is your factor of safety. They give you the number 2, 3, 4, 1,5. And D is your internal diameter. Okay. So keep this in mind, okay? The PC, pressure in the circumferential direction, you use longitudinal efficiency. I think this formula is in your formula sheet. Just double check, but it's very easy. S is your factor of safety. Eh? There's a longitudinal stress now. You can see the longitudinal stress. Okay, we're talking about the force in the circumferential direction. That causes your things to rupture. Okay, the longitudinal now will cause the circumference to rupture. All right. That's how that works. Just the opposite now, and then you end up with PD of 140. Remember, L is a longitudinal, the long one. The large number must be here. Okay. The other one would be opposite. Pressure in the longitudinal direction, or stress in the pressure in the longitudinal direction. Okay. Allowable pressure is 4. Check here, slightly different now. This one is 2. Okay. So this one is 4 times the stress in a longitudinal direction times the wall thickness times circumferential efficiency. Watch out. Be careful. Upon factor of safety times D. If the question asks you what's the maximum allowable pressure, you always take the smaller value for safety person. Remember, you're going to have two pressures. You're going to have PC and you're going to have PL. If the question says what is the maximum allowable pressure, the maximum one would always be the smaller value here because it is for a safety. It is for a safety, this thing, a safety perspective. Okay, so keep that in mind. Huh? Right, don't worry about spheres. We're not going to do that. Don't worry about all that. There's an example here. A cylindrical vessel has a diameter of 1.3 meters. Internal, read carefully. The small d now, that's what we want in the formula. 10 millimeter thick plate. Efficiency of longitudinal and circumferential is 75 and 25 respectively. Respectively mean the first value, first thing is for the first value. So longitudinal is for 75, circumferential is for 52. They're giving you the stress, 400 megapascals, factor of safety of 6. They want to know the safe internal pressure. Read carefully. They're not asking you for PC or PL. So you got to calculate both and you got to choose the smaller one as your answer. Like I taught you, right? You write down the formulas. You can start with any one first. Doesn't matter. PC or PL. Straightforward question, this is. Just put in the values. Here they're writing the efficiency. First one is 769. Use the next formula. You get 1,0. Of course, safe one will be 769. Very easy, eh? You're not worried about shrinkage type of problems where you're shrinking one inside the other. We won't do that type of thing. Right, and I think the last part to this thing is people where you can have thin cylinders now that rotate. Okay, an example now is your car, is your tires in your motor car. When you go to the blood bank, when you do a blood test, you take out blood, you put it into a glass tube, they send the glass tube to the hospital, into the lab, they rotate that glass tube at a very high speed or revs to separate the plasma from all the chochos in your blood, all your dirty blood. You check whether you got HIV or what test you done. So they rotate that thin tube. You notice when they pull out blood, you put it out in the test tube. Test tube is made of glass. Yes, I never said thin cylinders is only steel. It can be made of any material. Long as that ratio is satisfied, D over T is greater than 20, it's classified as a thin cylinder. It can be made of any material. Okay, so those glass tubes where they put your blood in is also a thin cylinder, long as that diameter over T is satisfied. Okay, now you get some cases, guys, where you got a cylinder which has pressure and it rotates. Okay, many examples I just gave you now. All right, now what happens? Nothing major. You got a normal cylinder under pressure, so you use a theory I already taught you. Now if something is rotating, what force comes into play? Centrifugal force. So you just add the centrifugal part also. And then you calculate the total stress. Okay, so you can see it's mv square upon radius over here. Okay, density is rho, kg per meter cube. Tangential velocity is in meters per second. You can see why mechanics and all is important. All right, so they're just deriving the formula here for you people. And you end up with this equation, 3.10. Write it down. Take a photo. It should be in your book also. I don't know if your book covers rotating cylinders. I don't think so. Okay. So stress due to rotation. Listen what I'm telling you nicely. This is for rotating cylinders only. So the stress due to centrifugal rotation. Or rotation is rho, which is the density. It's not P, it's rho. Okay, it's the density times the velocity square. Rho V square. So if you got a case now where you got a thin cylinder under pressure, you use your normal formulas I already taught you. And if they tell you in the question is rotating, so you say plus rho V square. So you add that up. So the total stress will be your stress circumferential according to the formula I gave you already, plus rho V square. You're going to add the rotating component also. If the cylinder is not rotating, then you ignore all this. It's only one simple formula. You add to add the stress. You've got two stress parts now. You've got two stresses. One due to the internal pressure and one due to rotation. This is the one due to rotation. So read the question carefully, see what's involved, and then you answer. There's an example on rotating. Thin cylinder. This is only now rotating. You get three cases here, people. You get a thin cylinder under pressure, like a 5X here. I hope you listen carefully, eh? Very important to understand what I'm teaching. That's why you come to class, eh? You get three classes of problems for thin cylinders. You get a thin cylinder that is stationary under pressure. Okay, your deodorant can, fire extinguisher that's on the wall, use the normal theory I taught you. Okay, so that cylinder is under pressure, normal one, stationary, not rotating. Then you get another case where it's only rotating. There's an example 3.3 here. That means there's no pressure inside, it is only rotating. So what happens in this type of case? You ignore the first part that I taught you. There's no pressure inside there. So of course you don't worry about the pressure formula. So you use rho v square. It is only rotating. Okay, many examples in industry also. But this one is only rotating. It got no pressure inside. That's why they don't give you any pressure. You can read there in the question. Straightforward. So use rho v square. A steel rim, mean diameter 1 meter, rotates at 1000 RPM. Determine the circumferential stress induced if the density is 7,800. Yeah, easy. So this is only rotation. So the first thing I will write down is my rotational stress. Circumferential stress is rho v square. That's the first thing I write down. Have I got rho? Yes. Have I got v? No. So what is the tangential velocity? Remember, it's rotational is given in a question. So you convert the RPM to meters per second, use pi d n upon 60. There's the formula. Meters per second. Push that into there. Square. Watch out the square here, guys. 21.3. Okay. So the third part of it now is you got pressure and it's rotating. Then you add the first part of theory to this part of theory and you add the two stresses up and you get the total stress. Okay. Now, before we finish up, you get some type of questions also where you have inspection covers. I know you've seen these manhole covers also that you have on the streets. The people are taking those steel discs now. Of course, there are plenty of them in Eskom. In the this thing boilers. The boiler is quite huge, 6-8 meters in diameter. It has dirt that builds up, which you call scaling. You need somebody to go inside the boiler to do cleaning up. Otherwise, you're going to get khokhos in your water, etc. How will the guy go inside? You can't do welding now on the circumferential caps. So you use a temporary fastener. So use what they call an inspection hole. Okay, so it's a disc big enough for a man to go through. They bolt it along the circumference. You see all those bolts on your bus, the bus example, the bus wheels. They've got about 12 bolts along the circumference. It's also a very good example of what I'm trying to show you. Okay, so you have some type of covers that are not welded for obvious reasons. All right, and they are secured by means of bolts. Okay, so what do? Do you need to be scared? No. All you need to do is do a force equilibrium type of thing, like we done yesterday. The load W must be equal to the summation of loads that are resisting the wires. Yeah, now you got internal force must be equal to external force. So the internal pressure must be equal to the external pressure. What is external pressure? Is the stress in the bolts. What is the external force? The force in the bolts. Sometimes they give you 5 bolts. So you got 5 areas. I hope you're listening very carefully what I'm telling you. Okay, so it's nothing difficult. The force in must be equal to force out. You write that as an equation. Or pressure in is equal to pressure out. All the same thing. Or stress in, internal stress, must be equal to the stress resisted by the bolts. The internal force must be equal to the force outside, which is the force resisted by the bolts. If you got 10 bolts, the area pi d square upon 4 multiplied by 10. Keep that in mind. Very important. Other than that, guys, it's a very easy section. All right. Any questions on thin cylinders? before we look at some tutorial questions from anyone before I close the slide? Are you 100% clear on how you attack problems on thin cylinders?
Yeah, I think we're good, sir.
All right. You know, when you go to John Dory's and Ocean Basket, you want to order rice, your girlfriend wants, or your husband or your boyfriend wants fish, chips. Now, what do you do now? You got limited money in your pocket, you order a combo, isn't that so? Half rice, half chips with your fish. Combo. So you get some type of questions which is combo, where you got a pressure vessel under pressure and is rotating. But that is a combo type one. So you just add the rho v square, the circumferential stress part to it. That's all. I normally teach the students that way. When you go to John Dory's and Ocean Basket, you want chips, your mate wants a rice. You got limited bucks in your pocket, so you order a combo, half fish, half rice, rice, half chips. Okay, so it's the same thing like yeah. All right, guys. So if there's no problems with that one, everybody understand. I think it's a very easy section. I see once if you do some of the theoretical notes.
Sorry, sir.
Yes.
So what is the expression of rho? I mean the unit.
Sorry?
The unit of rho. That's P. That's rho.
Kg per meter cube. Kg per meter cube. It's density. Okay. All right. Okay, good. Thank you. Nice you ask. Page 508. Yeah, don't worry about questions where they're giving you strength. Just follow what's in your study guide. That's all. Read your study guide. Do what's in there. You get 100%. Provided that you're attending my classes. Right. So there's a lot of involved work in your textbook. So don't worry about all that. You've got good guidelines of what you must do. There's an example of a boiler tube there. Example 14.3 on page 518 of your textbook. Nice example for tests and exams. Okay, so don't let the diagrams and the questions and all make you scared. You follow what I taught you, you will you will be all right. Okay, follow the type of problems that I taught you, you'll be all right. Don't worry about interference fits and all that, what I didn't teach. Interference fit is like shrink fitting. I told you earlier on, do not worry about all that. Ignore all that. Check what questions are in your study guide, and then you follow that one. Right, exercise and problems. It's opening up. Just be a little bit patient. All right, P152, chapter 14. Do not worry about spheres. So this P14.1 is a soccer ball. So don't worry about all that type of thing. Do what I ask you need to do. Okay, so do not worry about spherical storage tanks. While we're talking about storage, okay, I think we're coming to that one. There's a nice example here now on example P14.8, P14.9. Let's concentrate on P14.9. Okay, very, very important. Yeah, you got some type of a storage tank. Remember, in our situation in South Africa, everybody is not lucky like us. You just open the tap and water come out. Okay, unfortunately, poor old people walk sometimes kilometers in their locations or whatever to get water, which is a basic necessity in life. After 25 years of democracy in our country, I tear when somebody tells me I have to walk 2 kilometers to get water from a storage tank. I don't feel good in my heart at all. It's not right. Okay, it's not right at all. Water is a basic necessity in life. It should be free actually also. But access to water, some people don't have water in their taps at home. But to walk for it. Look at the problems with all these khokhos in the water and all that. Okay, so what they do now in cases, people try to help, government, whoever, and they give them these storage tanks, Jojo tanks or whatever. Okay, and they come and top it up with the truck or something. So they have to walk to it. The storage tank is not coming to their house. People must be grateful for what we have also. People take, myself is included, we tend to take everything for granted. Yeah, we're lazy. We take everything for granted until the water is turned off. And then you see for one day what stress you go to. The toilets don't work, nothing happened. Right, people out there after 24, 25 years, people are still walking kilometers to go and fetch water. All right. So these storage vessels, they got water in it. And of course, the water has a specific height. Now read this question here, P14.9. I hope you mark it. Very important question, eh? A tall, open-topped standpipe or vessel has an inside diameter of that and a wall thickness of that. Okay, this is a typical one that they use in the rural areas. See how big the diameter is, 2.7 meters. Big. The standpipe contains water with a density of 1,000 kg per meter cube. Yeah, they're asking you what height of water will produce a circumferential stress of 16 megapascal. They're asking you the question backwards now. You have to get used to these things. It's just mathematics. No new theory. Same formulas. You just make H the subject of the formula. But where is H? Desai never taught me anything about H. Pressure vessel. It's not rotating. It's just standing. Where is the pressure? Huh? Maybe there's something wrong with Desai, yeah? Where is the pressure? Who can tell me where is the pressure? Raise your hand. Talk. Don't be scared. We all are learning. Desai is also learning. I don't know everything. I want you to think a little bit. We're talking pressure vessels. This is our subject today. Where is the pressure? Yeah, you got water standing in a tank. Anybody besides Foster? I don't want to hear Foster anymore now. On the light note, eh? Come, guys. Where is the pressure? Take a chance. Take a chance. Tatama chance. You're writing your test. You're taking a chance, but you don't study for your test. So why you don't take a chance now? Come, guys. Where is the pressure? There is a pressure there, of course. Where is the pressure? You got water standing on inside a pipe. Yes, somebody's talking.
I'm gonna give it a try.
Yes, go for it. That's why you are here. Where is the pressure?
Inside the tank.
Sorry?
Inside the tank.
Right, but how do you get the pressure?
Or you're going to use the formula for circumferential stress.
No. Circumferential stress is going to ask you for the PC. Where is the PC? That's what I'm asking. They don't give you any gauge pressure in this question.
Okay.
Where's the value for PC? That's what I'm asking. Looks like the question not giving you the pressure value. That's what I'm asking now. Is the question wrong, or how do we solve this problem? Nobody know. Okay, time is running now. Satoli? Don't want to talk to me. Okay. Right.
No, sir. I've been looking at the question, and I think the pressure might be concentrated at the center of the pressure of the cylinder, sir. I'm not too sure about it.
Okay. A hint is they're giving you this H. It's a height. Huh? Why are they giving me a height? Remember, ink is very expensive at TUT. Remember something in engineering. They never give you information in a question that you will not use. Never think you are Einstein that you can solve the problem without that data or fact that they are giving you in a question. I'm giving you another hint also. Always keep that in mind for engineering. Whatever they give you in engineering, the question, you'll always have to use that thing somewhere. 99% of the time. Okay, guys, we're running out of time now. This height here. Question is, where is the pressure? The pressure is not given. You have to calculate it. The pressure can be calculated by the formula used in fluid mechanics called rho GH. I hope you're writing, eh? Rho is density. G is gravitational acceleration, 9.81. And H is the height of the fluid in meters. Now you can calculate what the pressure is here. Very, very important, because when you do design work for the storage tank, you must use that formula. So pressure is equal to rho GH. Height H is the height in meters. You put it into that simple formula and you get the value for pressure. Thereafter that, you can work as you normally work. All right. So keep that in mind. Huh? All right. So you can get some questions so keep that in mind. Huh? Whenever they give you a height, always remember what Desai taught you, eh? Rho GH. Right, so go over that P14.9, important question. Not many here in your textbook. P14.16, very important question. It's about 4 or 5 only, I think, here, guys. Won't take you long. It's a short section, this. Do not worry about the questions with strain gauges and all, eh? What's in your study, guys, what you do. Okay, I'll not ask you anything more than that. All right, guys, my voice is gone. There's a lot of other questions. Do not worry about shrink fritting, interference and all. We're not done all that. Temperature loading and all, don't worry about all that. Eh? Spherical vessels, don't worry about all that. Right, guys, over to you now. My voice is gone. Any questions from your side? Anything you're unsure about? You feel now you got the strength and ability to attack the questions now on torsion, axial loaded members, which is the same thing as torsion that we done yesterday, and thin cylinders. Any questions from your side? Anyone? I will put the recordings up now. Don't worry. No, everybody is happy. Everybody is comfortable.
Sorry, sir.
Okay, good.
Yeah.
All right then, guys. Thank you very, very much for attending. So we meet again next week, Wednesday afternoon, to do the springs quickly. And then we spend most of the period on tutorials. Questions must come from you guys, please. Feel free to share things. Nobody's picking on anybody. We're all learning. I'm also learning. Nobody knows everything. Bring your problems here. Let's talk about it. Let's learn. That's the way you learn. Do not be shy. My boyfriend or my husband is sitting in the same class as me. What he's going to think of me. Maybe he himself don't know. And he's shy to ask. So ask questions. You come here to learn. That's why we have classes. Right. So continue with the tutorials. Prepare for your test also. Next week, Thursday, write the test in class. Prepare for that. Start doing these tutorials. Not many questions you got in your textbook. And give it your best shot. Do the worked examples first. You know the procedure. After that, build up your knowledge. And then after that, do the tutorial problems in your textbook. The answers are given. Teach yourself also. Contact your friends also. You also learn from each other in your own home language. English is not everyone's language. Okay? And give it your best shot. All right, guys. Have a nice day. And I see you guys now next week, Wednesday, for the final tutorials period. Okay, guys. Thank you once again and goodbye.